So I'm Kevin Duarte. I'm going to present Capsule Networks for Video Understanding, my dissertation. So video understanding is a very large area in computer vision. It's been heavily studied, mainly just studies problems dealing with video. In this dissertation, we mainly deal with these problems. So video action detection, video object segmentation, text-based video segmentation, and self-supervised multimodal learning. So I'll go into detail about each one of these problems. So first, video action detection. So this problem, you're given a video, and the goal of the problem is to first classify the action. So example, in this case, the class is cricket bowling, and then also to spatial temporally localize the action. So this can be done with either bounding boxes, as seen in red, or pixel level segmentations, as seen in blue. It has several challenges. So one is that of crowded scenes. So for example, here we have many different people within the scene, but only one of them is doing the action of interest. And it could have multiple actions from actors per video. So for example, salsa spin and fencing always require at least 2 people to perform that action. So video object segmentation. In this problem, again, you're given a video, but this time you're given the first frame segmentation. And the goal of the problem is to segment the object of interest throughout the video. So in this case, we want to segment this deer in all the frames of the video. Again, there are many challenges. So one is that of similar objects. So for example, all these birds look quite similar, but you have to differentiate them using that first frame segmentation. Small objects, as you can see in this video, this person is wearing a helmet or a hat, and that is very small relative to the entire size of the video. Issues of occlusion. So if an object moves behind another object, we still have to segment it in the case of this tiger. And also fast motions. So either the camera could have a lot of fast motions or the object can be moving rather quickly in the video. Next is text-based video segmentation. So in this problem, you're given a video and you're also given a natural language query. So in this case, we have the video and we have the text blackbird in a cage. And what we want to do is segment what the text is describing. So in this case, the blackbird in the cage. So there are several challenges here. So one is trying to understand the textual semantics of the query. So in this case, we have to understand what color the ball is to segment it. So we have to know what green is, and we have to understand what baby rolling is, right? We have to understand that the baby is rolling on the floor. And then also, again, there could be multiple similar actors, right? So in this case, we have 2 girls bouncing on a red ball, but now we have to be able to differentiate them just using the descriptor. So the girl in white versus the girl in red. Yeah. And then the last problem we deal with is self-supervised multimodal learning. So in this case, we're given a video, audio, and corresponding caption. So in this case, it's a video of placing chicken in oil, and we would have the audio for that as well. And the goal for this is to learn a joint multimodal representation for each of these modalities. This is a very challenging problem. First reason, it's dealing with large-scale noisy data. So often, sometimes the text caption doesn't correspond necessarily with the video. And the second is that there's no ground truth handmade annotations, right? So we have to deal with those 2 issues. So now that I've talked about the problems, I'm going to talk about how they're conventionally solved using convolutional neural networks. So that's the current gold standard for most vision problems. And it's been shown, the CNNs have been shown to achieve strong performance with large amounts of labeled data and with very deep network architectures. And in most video tasks, some variant of a 3D CNN tend to achieve state-of-the-art results. However, there are some issues with CNNs. Specifically, that CNNs do not explicitly model entities within an input. So to illustrate this, we have 2 images here. The image on the left is an image of a face, and when given to a CNN, the CNN would have some sort of feature representation for the face that would say, okay, there's an eye, there's a left eye, there's a right eye, there's a nose, and there's a mouth. And then the CNN will predict that there is a face in this image based on those features. But when given the image on the right, again, the features would show, okay, there's a right eye, there's a left eye, a nose, and a mouth. The CNN would also predict that there's a face in this image. But if you look at this image, we know that there's no face. There's just the different parts of the face all reordered in the image. So in this case, if the CNN was able to model entities, then it would correctly predict that there is no face in this image. To solve this issue, there's been a new network architecture called Capsule Networks. So what Capsule Networks do is they try to add extra structure to model entities within an input. So the entities are modeled as groups of neurons, and routing by agreement is used to model the part-to-whole relationships of these entities. This takes inspiration from inverse graphics, which I'll talk about now. So in computer graphics, what happens is we're given some objects with certain instantiation parameters. So for example, a rectangle and triangle at these positions, at these angles, and then a rendering function is called to generate an image of the rectangle and the triangle. Well, inverse graphics is the opposite. We're given an image, we call an inverse rendering function, and then we obtain these instantiation parameters. You could view computer vision as basically this inverse graphics problem, where we get an image and we try to understand the different properties or parameters of the objects in this image. And that's what Capsule Networks try to do. So to do this, capsules are try to represent these instantiation parameters using a 4x4 pose matrix, and also an activation. So this activation is between 0 and 1, and it is a probability of existence for that given object that the capsule represents. Capsules in lower levels vote for capsules in higher levels. These votes are predictions of the parts to the wholes. And votes are grouped together using a routing by agreement algorithm. So as I said, routing attempts to find these part-to-whole relationships. So to illustrate this, again, we'll go back to this original two images. For the image on the left, we have the different parts of the face, the eyes, the nose, and the mouth. Each one will vote on the, let's say, center of the face. So for example, the left eye would vote the center is at this position, the right eye would vote this position, and the other parts of the face would vote at this position. And the routing algorithm will find that there is agreement between these votes. So the capsule network will predict that there is a face in this image. For the image on the right, the left eye would vote that the center of the face is at this position, the right eye would vote this position, and the other parts would vote correspondingly. But in this case, there is no agreement. So the capsule network will predict that there is no face in this image, right? Which is better than the CNN. Capsule networks are composed of layers of capsules. Each layer routes its information from one layer to the next. So for a given image, we have some encoder, which generates a set of initial capsules, and those represent the lowest level objects in the image. Then routing by agreement generates a second set of capsules, and so on and so forth to create a deep capsule network. Ideally, the final layer of capsules will represent all the entities within that entire image or scene. And in the works I'll be presenting today, we tend to use the EM routing algorithm. So this algorithm achieves strong performance, but it is an iterative procedure that clusters votes. And for that reason, it's computationally expensive. So now that I've explained capsules and routing, this is an overview of the different parts of my dissertation. I'll begin with action detection with video capsule networks. And this was published in NeurIPS 2018. So up to this point, capsule networks achieve good results when classifying small images, like MNIST images or small number of images, but they're rarely applied successfully to high dimensional data, like large images or videos. And the main issue, as I mentioned earlier, is the computational cost. And because of this computational cost, deeper networks cannot fit into memory. So to illustrate this, I'll first talk about convolutional capsule layers. So given a set of input layer of capsules, right, where there's a height, a width, and some time dimension, because we're dealing with videos, convolutional capsule routing obtains a receptive field of capsules, then uses transformation matrices, some learned transformation matrices, to generate a set of votes for these capsules. Then the EM routing algorithm takes these votes, clusters them, and generates a set of output capsules, which are placed at this position in the feature map. So as you can see, that there's a large amount of votes being generated that have to be grouped together or clustered at each position of this map, which is extremely computationally costly. To solve this, we have two simplifications. One is we have the same transformation matrix for all capsules of the same type, and the second is capsule pooling. So going back to this figure, the first change is the transformation matrix. So now each type shares the same transformation matrix within the receptive field. So that reduces on the computation. The second is capsule pooling. So here for each receptive field, we average the capsules within that receptive field so that we only end up with CL capsules. Then when we multiply the transformation matrices and get these votes, we have a drastically fewer number of votes to route. And this allows us to fit deeper networks into memory. So with this capsule pooling, we're able to propose a video capsule net architecture. So the input of this architecture is 8 frames of 112 by 112 video, and the output is a set of localization maps for each of the frames. And this is an overview of the architecture, which I'll go into detail now. So first we have an encoder, which takes the input video, passes it through a series of 3D convolutions to obtain feature maps. These feature maps are then transformed into our initial capsule layer, which is 20 by 20 and has 6 temporal steps. Then we have the convolutional capsule routing layer with the capsule pooling to generate our second conv caps layer. This is followed by another routing layer, but this is a fully connected routing layer to obtain the class capsules. And here we have one class capsule for each of the corresponding ground truth classes. So if there's 24 classes, there will be 24 class capsules. The decoder is the second half of the network, which takes these class capsules, masks them, which I'll describe later, and then passes them through fully connected and 3D transpose convolutions to obtain the localization maps. There's also skip connections from the input from the convolutional capsule layers to obtain to be able to keep the spatial temporal information for this localizations. So we make use, as I said in the decoder, we use capsule masking. So what this operation does is during training, we zero out all classes except for the ground truth class. So for example, if the input video has the golfing class, then during training, we'll mask out all capsules that don't correspond with the golfing class and only use this golfing capsule to generate the localization. At test time, we mask out all capsules except the predicted class. We find that this allows us to generate better segmentations and more class-specific segmentations. So our network is trained end-to-end with a sum of 2 losses. The first is a classification loss, which ensures that the ground truth class activation is higher than the other capsule activations, and a segmentation loss, which is a binary cross entropy, which tries to segment the actor in the video. The total loss is a weighted sum of the 2. So we evaluate this on 3 action detection datasets, and we find that we get very good action localization performance across all 3 datasets. So here are some qualitative results. So as you can see, so in this case, the red is the ground truth bounding box, and then the blue is our localization, and this is the class on the bottom. So as you can see in the second case, even when the actor is moving halfway across the screen, our network is able to correctly localize the child biking. And then these last 2, even when there's quite a lot of motion, our network correctly localizes these actors. So for this first part, we have generalized capsule networks from 2D images to 3D videos. We propose capsule pooling to make the routing operation more efficient. We have an end-to-end human action localization method using capsules, and we get state-of-the-art results on 3 datasets. So action detection requires the localization of specific actions, right? For example, diving or golfing or biking. So the question is, can we localize arbitrary objects or actions? This more general problem is called video object segmentation. This brings us to video object segmentation using capsule routing, and this was published in ICCV 2019. So as mentioned earlier, video object segmentation, you're given a video as well as the first frame segmentation, and you want to segment that object of interest throughout the video. So how do we do this using capsules? Well, we know that capsules can model entities or objects within the input, and routing by agreement finds similarity between these entities or objects. So we can leverage these two ideas to make a video object segmentation method. So the first thing we do is extract capsules from the video as well as the segmented first frame. The video capsules would model objects within the video, and the frame capsules would model only the object of interest within that first frame. And then we could use routing to find agreement between these two sets of capsules. So pictorially, here's the described method. So given a video, we have a video encoder to obtain our video capsules. Given the first frame segmentation, we have a frame encoder, which obtains our set of frame capsules. Then we have a routing operation, which conditions the video capsules. And finally, we have a decoder network, which takes these conditioned capsules to generate our segmentation mask. So now how do we do this this routing? So we can use the standard EM routing, and this achieves good results, but more can be done. What we do is we adjust the routing algorithm so that we can find agreement between two different sets of capsules. Ideally, the routing should condition the video capsules based on the frame capsules and not just route all the capsules together, regardless of where their origin is from. So I'll now describe the attention routing mechanism we propose. So given our video capsules and our frame capsules, we obtain a set of votes. So the value votes, the key votes, and the query votes. So this terminology is similar to the to attention, if you're familiar with that. So from these query votes, we use EM routing to generate a set of query capsules. Then, using the query capsules and the key votes, we try to find a similarity between these two. So we take the Euclidean distance between these query capsules and key votes to obtain a distance matrix. And then we have a softmax operation to obtain assignment coefficients. And these assignment coefficients determine how much information from the video capsules, or these key votes, should be passed to the next layer. Ideally, only capsules corresponding to the object of interest will be passed to the next layer. So once we have these assignment coefficients, we take the value votes and we pass them through the M step of the EM routing algorithm to obtain our conditioned set of video capsules. So I've described the routing mechanism. So here is the overall approach. I'll describe each portion now. So we start with the video encoder. So this is similar to the encoder video capsule network. The main difference is we have a higher spatial resolution, 1028 by 224, and we replace the 3D convolutions with 2+1D convolutions. We find that this improves performance as well as speed. Then we have the frame encoder with a memory module. So the frame encoder uses 2D convolutions to obtain features. Then these features are passed through a memory module which consists of a convolutional LSTM. This memory module is useful for dealing with occluded objects or objects that leave the scene. From this memory module, we generate a set of frame capsules. Then we pass the video capsules and the frame capsules into the attention routing. So, and then once we have these conditioned capsules, we pass it through our decoder network. So this is composed of transpose convolutions, and it has skip connections from the video capsule layer. And this outputs the segmentation mask for all frames of the video. So one issue that I mentioned earlier is the issue of small objects. So you can see this video here, this person here is quite small when compared to the rest of the video, the frame. So what we do is we propose a zooming module, which attempts to zoom in on that actor within the first frame segmentation, as well as within all the video frames. Then, using this crop, we can pass this into our Capsule VOS architecture to generate the output segmentation. This allows us to deal with these small objects and generate very fine-grained segmentation masks. So our network is trained end-to-end. We use 2 segmentation losses, binary cross entropy, as well as a dice loss. And this dice loss lets us obtain more fine-grained segmentations. And we also trained the zooming module with an L2 loss for the bounding box that the zooming module predicts. And the entire pipeline is trained end-to-end using the sum of all these losses. So here are some quantitative results on the YouTube VOS dataset. As you can see, we achieve state-of-the-art results when compared to previous methods. One thing, though, we achieve much faster speeds, almost 2 times as fast as these other offline methods. So here's an analysis of the speed. So as you can see, we achieve only about 1% less than the online version of S2S, but we have a 100-fold increase in speed, which is very useful for this video object segmentation task. Here's some qualitative results. So you can see that our network is able to finally segment these objects, even when, in this case on the right, when the fox is moving quite quickly, our network is able to keep track of the fox and segment it. And then when there's multiple objects, our network can deal with that as well. And as you can see in this bottom right example, even when there's objects that look very similar to the objects of interest, we're able to correctly segment them. So now I'll show the effects of the memory module. So in this video sequence, our network without the memory module correctly segments the bear in the beginning, but then the bear becomes occluded by the tree. And then when the occlusion ends, the object is not correctly segmented because there is no memory module. However, with the memory module, again, we correctly segment the bear becomes occluded, but after the occlusion ends, we're able to correctly segment it, even after that very long sequence of it being occluded. So here are some video examples of that. So you can see that the bear here is partially occluded by these logs, and that the woman segmented by the pink is correctly segmented after this occlusion. I'll show some examples of the effect of the zooming module. So as you can see, these 2 people on the ball are very small compared to the rest of the frame. Without the zooming module, we can see that even by frame 20, we're incorrectly segmenting this ball. And by frame 90, these two, this person and the ball, are completely lost. However, with the zooming module, we can see even by frame 90, we're able to segment all 3 objects of interest, and the segmentation of this person is still quite fine-grained. So here's some video examples. You can see it works on a variety of different objects, and even when there's multiple small objects, we're able to correctly segment them. So in summary, we propose a new attention routing algorithm. We propose a video object segmentation method that uses capsules, and we choose state-of-the-art results on the YouTube VOS dataset. So in this work, we've segmented objects based on the first frame. However, what if we don't want to have to segment the first frame of every video we want to have segmentations for? How do we have a different prior? Well, what if we instead use a natural language sentence to segment an object? This brings us to the third part, text-based video segmentation with visual textual capsule routing. And this was published in CVPR 2020. So in this problem, we're given a video sequence and a text query, and we want to localize the object or actor based on this sequence. So for example, for the same video, we can have the dog is walking around the red cones, and we would segment this dog, and the woman in the green top standing on the left, and we would segment this woman. So our overall approach is as follows. We create a set of video capsules and text capsules. We use capsule routing for textual conditioning of the video, and then we produce segmentations for all frames of the video. Pictorially, this is seen as follows, right? We have our input video and a video encoder to generate our video capsules. We have our text query and the text encoder to generate text capsules. We have a visual textual routing algorithm, which tries to find agreement between the video and the text to obtain a new set of capsules. And then we have a decoder, which generates a segmentation mask for the actor or object of interest. So the basis of our visual textual capsule routing is that both the video and the sentences contain the same entities. For example, we have the visual entity of this brown dog and the textual entities, sitting brown dog, the visual white dog, walking white dog, and then the woman in the green top. So based on this, how do we perform this routing task? So given a video, what we do is we generate a grid of video capsules. So in this case, each location on the grid corresponds with the object at that location in the video. So for example, the woman in the green top is located in this capsule, in this region. The brown dog is located here, and the white dog is located here. Then we get our sentence input, and we generate a set of sentence capsules. And what we try to do is find agreement of these sentence capsules at each location in this video capsule grid. So suppose we get these 3 locations for these different objects in the videos capsules, and we get the sentence capsules, and we pass this through a routing by agreement algorithm. We would find, okay, these 2 sets of capsules have no agreement because they don't have the same entities within them. Again, there's no agreement because the white dog does not have agreement with the sentence. But when you're at the location of the woman in the green top, standing on the left, then there is agreement. And the output capsules would have higher activations. So now I'll describe the visual textual capsule routing algorithm. So in this case, we're given the video capsules, poses, and activations. We're given the sentence capsules, poses, and activations. And we're given the transformation matrices, which generate the votes from the respective poses. This is the routing procedure. We first start off by getting the votes for the sentence capsules. Then for each location on the grid, we obtain the votes of the video capsules at that position. We then combine the activations and votes for the video and sentence capsules, and we pass it through the EM routing algorithm. And this outputs the capsules, the higher level capsules, which have the agreement between the sentence and the video. So this is our network architecture. So I'll go through each part now. So I'll start with a video encoder. Here we have an input video of 4 frames consisting of 224 by 224 resolution. The video encoder consists of an I3D network, which generates a set of feature maps. And then finally, we obtain our video capsules using a convolution operation. And this is a 20 by 20 grid with 8 capsule types each. Then we have the sentence encoder. So given the sentence, we use Word2Vec to convert them into 300-dimensional embeddings. We pass these embeddings into a set of 3 parallel 1D convolutions, each with different kernel sizes. And we apply max pooling to obtain a single feature vector of length 300. Then we pass this feature vector into a fully connected layer to obtain our set of 8 sentence capsules. Once we have the video and sentence capsules, we pass this through our visual textual routing algorithm. And the output is a set of actor capsules. In this case, we have 8 capsule types because the data set has 7 actors, and we have an additional capsule type which corresponds with the background class. We find that this class capsule correspondence helps during training. And this is mainly due to the masking operation. So we perform this capsule masking, which was brought up in video action or video capsule net, where we mask out capsule types which are not relevant to the query. Then we pass these capsules into the upsampling network, which consists of 5 convolutional transpose layers. And the output of this is a binary segmentation mask for all 4 frames of the video. So our network is trained end-to-end using 2 losses. So the first is a segmentation loss. We use binary cross-entropy loss. The second loss, although it's not necessary to train a network, we find it improves results. It's the classification loss. Again, it's a margin loss, which tries to ensure high activations for the actor capsules which correspond with the ground truth class. And the final loss is the weighted sum of both of these, classification and segmentation losses. So here are some quantitative results on the ATT data set. We achieved strong performance across all metrics, especially when the overlap is high. Here's some qualitative results. So in this example, we have 2 sentence queries. The person is walking backwards while being followed by the dog in green. So you can see we correctly segmented the person. And the black dog is crawling. Again, we correctly segmented dog. This first row is trained only using segmentation masks on keyframes. And this second row is trained using bounding box segmentations on, or bounding box boxes on all the frames of the video. So as you can see, the second case, it's blockier, the output. However, we find that training on all the frames of the video leads to slightly better results when you want to purely localize these objects. So this is shown in this example, where when only training on keyframes, we incorrectly, or we do not segment this dog on the left, but when training with all the frames, we correctly segment this dog. So here are some video results of a parrot jumping on a couch back and the baby in white climbing up the stairs. So as you can see, our network is able to correctly segment the bird and the baby. And you can see these segmentations are actually quite fine-grained. So in summary, we propose a novel visual textual capsule routing method. We also propose an end-to-end action video segmentation method using capsules, and we achieve state-of-the-art results on ATT dataset. So up to this point, the 3 methods that I've showed, they've all required full supervision. By that I mean they required annotations that were human-generated. So for example, for action detection, we require this class name as well as the localization. And for the text-based video segmentation, we require these segmentations as well as these human-generated sentences, which correspond with the segmentations. However, this requires usually a lot of time, a lot of manpower, and a lot of money to obtain these annotations, especially if we want a lot of video annotations. So the question is, can we learn capsule representations in a self-supervised manner, such that no annotations or human-generated annotations are required? This brings us to the last part, self-supervised multimodal capsule networks. So for self-supervised multimodal learning, we can leverage large-scale data. So in this case, we're given video, its audio, and the text caption. And the goal is to learn a multimodal representation between the 3. So how do we do this with capsules? So again, we know that capsules with routing could find entities or concepts within an input. What we do is we extract capsules for each modality, so the video, audio, and text. We have a shared network which routes the capsules to learn higher level concepts within each of the modalities. And then we map them to a joint representation space. And this joint representation space is enforced using a contrastive loss, which tries to minimize representation distances across the different modalities. So this is our capsule framework, and I'll go through each part now. So we begin by extracting some sort of low-level features. From the video input, we extract visual features using 2D and 3D convolutional neural networks to obtain a single feature vector for the video. For the audio features, again, we use a 2D CNN, which extracts a single vector representation. And from the input text, we use word2vec. Once we have these features, we obtain our set of primary capsules. So these these features are passed through a linear layer to obtain a set of capsules. In this case, we extract a set of 128 capsules for each modality. This is much more, many more capsules than we used in previous works. The reason for this is we have such large-scale data that we need to model a larger amount of entities or objects. So for that, we need, more capsules. Then from the primary capsules, we use routing by agreement to get a set of activations and use these activations to weight the capsule outputs. So this routing operation obtains a new set of capsules whose activations are used to weight the primary capsules, which are used to generate our final representation. So the question is, how do we do this routing? So as previously stated, the iterative routing approaches like EM routing are extremely computationally costly because the iterative procedure takes up too much GPU memory. So what we do is we propose a more efficient solution. We use self-attention as a means to find agreement between these capsule votes. So now I'll talk about our routing by self-attention method. So given a set of capsules, we could obtain the poses and activations of these capsules. Then we weight the poses based on the activation. This ensures that capsules with low probability do not affect the routing procedure. Ideally, we would only want entities that exist in the input, i.e. those that have high probabilities to affect how information is routed. Then from these weighted poses, we obtain a query key and value, and we pass these into the multi-head attention block. And this multi-head attention block is a standard attention where we get the query and the key to get an attention matrix, and then this is multiplied by the votes, and then followed by nonlinear layers to obtain a set of output features, which are the pose vectors of the next capsule layer. Then from these pose vectors, we have a linear layer and with softmax activation to obtain our activation probabilities. And we can group these two to get our output capsules. So once we have these output capsules, we generate our joint embeddings. This is done by getting the poses of the capsules and passing it through a linear layer. And then these final output embeddings are trained using a contrastive loss, which I'll describe now. So the contrastive objective attempts to push modalities from the same time frame together. So I'll show an example here. So suppose we have this same chicken video, placing the chicken in the oil, and we have another video of adding black pepper and sea salt. So given those two videos and then the text, we can map these into our embedding space. And what the contrastive objective tries to do is first push modalities from the same time step together. So in this case, this video on the left and the text on the left are pushed together. The embeddings for those are pushed together. And the video on the right and the embedding for the text on the right are pushed together in this embedding space. The second thing it tries to do is push embeddings from different time steps apart. So in this case, this video of frying chicken should be pushed away from the embedding of the sentence adding black pepper because there is no black pepper or adding black pepper in this video. And likewise, these two different time steps should be pushed apart as well. So formally, we use the mass margin softmax loss, which is a contrastive loss. And what it tries to do is ensure that the dot product or similarity of two modalities, so in this case, video and audio, are closer together by some margin delta. The total loss is the sum of all pairwise losses. So what we do is we get each pair of modalities, so video audio, text audio, and video text, and we sum up the losses for all the pairs to ensure that all the modalities are mapped to the same multimodal embedding space. To train our system, we use the how to 100 million dataset. So this dataset contains about 1.2 million instructional videos. So this is much larger scale than all the previous datasets we've used, which had at most 10,000 videos. So this is orders of magnitude larger. It spans 23,000 different tasks, and these different tasks can include things like cooking food, working on cars, home and garden, health, sports activities, things like that. To evaluate our method, we evaluate on two downstream tasks. So the first is zero-shot text-to-video retrieval, which is done on the UCOOK2 and MSRVCC datasets, and zero-shot action localization, which is done on the cross-task and mining YouTube. For these two tasks, we decide to use zero-shot evaluations, which means that we're not fine-tuning our method on these new data sets. We're only training on the how to 100 million and applying our trained model on these data sets and tasks. So for video to text or text to video retrieval, we can see that our method achieves state-of-the-art results, especially when using a strong visual backbone to obtain those initial visual features. For action localization, again, our method outperforms previous methods on both data sets. One thing we also look at is we try to compare our routing method, our self-attention routing, with previous routing methods. So we see that not only does our routing method outperform in terms of recall on this text-to-video retrieval task, but it's also much more efficient in terms of memory as well as runtime. Especially when compared to these iterative procedures, dynamic routing and EM routing. So this really lets us deal with larger scale problems, which these previous routing approaches were not well suited for. So now I'll show some qualitative results for text to video retrieval. So given the query add oil, vinegar, lemon juice, and garlic to a bowl, these are the top 3 predictions from our network on the UCOOP2 dataset. So as you can see, so the green denotes the correct prediction. So here they're adding, oil and what looks like vinegar to the bowl. So our network gets it in the second place prediction, but even for these other predictions, you can see that the semantics are still there. They're adding something to a bowl. It just happens not to be the correct items. Again, you can see another example here. We correctly predict the chop and add fresh basil and stir. Our network correctly predicts it as the top 1 retrieval. And then also we get other similar looking videos in second and third. And then here are some other examples where our network is able to correctly predict or retrieve these videos using the text query. One additional analysis that we perform is we try to attempt to learn what these capsules are learning. So in this case, we do not have supervision, right? This is all self-supervised. So we don't know the correspondences of what entities these capsules are learning. In this case, we find out that the capsules do learn meaningful representations. So for example, capsule number 81 is able to learn what games are. So in this case, video games. We can see that other capsules represent other things. So there's a capsule that learns what people are, a capsule which learns what pots and bowls are, a capsule for pets and animals. Overall, we find that most of the capsules correspond with a single object or entity. These things or concept. These things can be very general, things like outdoor activities or cooking, or these things can be very specific, like cars, vegetables, or pots and bowls. And this is all done without supervision. So these concepts were able to be learned without any supervision. So in summary, we propose a novel self-supervised multimodal capsule framework. We propose also a computationally efficient self-attention-based routing method. And we achieve state-of-the-art results on 2 zero-shot tasks, text-to-video retrieval and action localization. So now that I've talked about all our work, one question is, how can this be extended, right? What else can we study with related to capsule networks and in video understanding? So one potential avenue of research would be to separate spatial and temporal routing. So for our first 2 works of video action or video capsule net and the capsule VOS, we use 3D convolutional capsule routing. But you can separate this 3D routing into routing in just spatial dimension, so the 2D routing followed by a 1D routing. This would be analogous to converting 3D convolutions into 2+1D convolutions, which has been shown to be beneficial for the learning task. The second is the inclusion of additional modalities. So we were able to show that capsule networks can work well for video, audio, and text, but there's other modalities like optical flow or perhaps depth in images. And optical flow has been shown to be very useful for different video tasks. So this is another potential use case for capsules. Another question, which is not, which has still not been fully answered, is how to best merge capsules from different modalities. So in our visual textual capsule routing paper, we merge them using the routing operation. We merge the video and the text using our proposed visual textual routing. And in our last work, we merge them. We technically don't merge them, but we share routing weights so that each of the modality capsules from each of the modalities learn the same or similar representations. So the question is, how is there a better way to merge these capsules, right? And we could look to these multimodal transformer works, which have shown very good results in merging, video and text. And the last, one last potential avenue for future work is related to capsules specifically. So one big issue with capsule networks is the computational cost, and that's, I think, one of the main reasons why capsule networks are not more widely used. And really, we should try to improve how we should try to reduce the computational costs of capsule networks. Two possibilities would be, one, to generate, improving how we generate these initial capsules. Generally, it's just using a fully connected or a convolutional layer to generate a large set of capsules, but this is very, memory, inefficient. And then the second possibility would be to have a more efficient routing algorithm. Of course, we propose our self-attention routing algorithm, which is efficient, but there can always be improvements on that. So I think that's this last 2 points are, I think, very important if we want to, have capsules to be used in more, more vision and video tasks. So in summary, I began with, the generalization of 2D capsule networks to 3D capsule networks and proposed a video capsule network for action detection. I showed that capsule networks can be applied to video object segmentation using our proposed capsule VOS network. We applied capsule networks to the multimodal domain of text-based video segmentation using visual textual capsule routing. And then lastly, we showed that you can train capsule networks without human annotations in self-supervised multimodal capsule networks. Thank you, everybody. And yeah, so here are some selected publications.
Okay, very good. So are there questions from the audience? So let me get started, then people can think about. So one question I have, that this whole routing issue is not there in the CNN, right? So CNN also has layers. You go from one layer to other layer, and as you explained, the notion of routing is that CNN looks at a local neighborhood and get the response to next layer, but routing is looking at the whole image and getting agreement and so on. So now this attention does that in a way, right? A self-attention, you get these. What is the difference with the routing, because with the capsule, because as you keep, you demonstrated that routing is a big bottleneck, it's time consuming and a lot of things there. So why do we still need the capsules and routing as compared to just attention?
Right. So I would say if you just use attention, then one issue is that really attention is you're given a sequence of feature vectors and you output a sequence of feature vectors. And in those individual feature vectors, then each activation corresponds with some, let's say, feature, right? With capsules, you have a bit more in that we are grouping these sets of features together so that we have multi-dimensional descriptors of whatever entity they're describing. So that's that can be more, you know, a more powerful representation than just having a single feature vector where we don't know which of these activations correspond with what object. With capsule networks, we know, okay, this capsule corresponds with a single object, and all the dimensions of that capsule correspond with a single object. So that's one part. The second is the difference between, let's say, attention versus, let's say, the dynamic routing. So the main difference is that dynamic routing is kind of, you could think of it as like a more bottom up. So basically from the predictions of the individual capsules, we get the representation of the whole object, whereas attention basically is, we get, again, predictions from these parts or these feature sequences, but we already have the notion of what the whole object is, right? So that's how they find agreement and attention, if that makes sense. So yeah, so that, I guess that's
okay, good, very good. Yeah, questions from the audience? Okay, so yeah, maybe from the committee, yeah, Dr. Davis, you have a question?
Yeah, I was just curious. You mentioned other modalities and optical flow. What is optical flow?
So optical flow is basically finds the, I guess, change in pixels over time. So given two frames, let's say there's some movement in those two frames, it tries to find the direction of the movement. Between
There's like a vector associated with it. Okay.
Right.
Thanks. Yeah, that makes sense.
So expanding on like Dr. Shah's question, difference between CNN and this routing, right? So I have a follow-up question, but before that, so you have low-level capsules, you perform routing, they vote, and then you create the high-level capsule, right? But this process is, if you think about self-attention, then again, you're doing the same thing, right? You are selecting how much of each of these lower-level capsules, or you can say features, you want to use, and then you transform them to like a high-level feature. So in that you can say that, okay, that's a high-level capsule. So then what's the, so you understand, like in that sense, it's the same thing, but still there is some difference. So can you expand on that? What exactly is
I
that?
think the one thing he's saying that there's a grouping, right? The grouping is not there in the attention, is that right? Yeah, I mean,
Yeah.
I'll give an answer, yeah.
Right. There's no grouping there. So in attention, what you have is, let's say, a sequence of features, and then you find your agreement, right? And you obtain an output sequence of features, right? So basically, for each feature, you attend based on the other features. In this case, but ultimately, the output is just a single feature vector, let's say, at each time step. In terms of capsules, we have groups of neurons at each time step, right? So what we would have is, instead of, let's say, 128 dimensional vector, right, where each dimensions of the vector correspond with some object or entity, with capsules, we have, let's say, 8 capsules, 16 dimensions each, or yeah, 8, let's say we have 8 capsules with 16 dimensions each. And so we have 8 entities, right? Each is described by that multi-dimensional vector, right? So I would say the grouping of these activations is really what makes capsule networks different from attention. There's some smaller differences, but yeah, I would say that.
So let's so what if you, so this is kind of, you are doing local grouping and then creating the next level, right? And in transformers or self-attention, you take everything and then you go to the next level. But what if you do the same thing with transformers as well? You group locally and you keep grouping, and then, so will it, do you think, will it be the same thing or still?
It'll be similar, right? And I think that such an idea could work, perhaps making it, more efficient than the standard routing operation. Yeah, I guess you could do something like that ultimately. Yeah, it's difficult to say how much better it would be than let's say some iterative routing procedure in terms of performance, but yeah, I mean you could do something like that.
Yeah, so I think that's the point. Like you had hidden those slides where you are showing that how this EM works with the
Right.
the votes depend on the grouping, is right?
Right.
If the cluster is tight, then votes will change. So that's probably is the main difference here, right? It's more dynamic.
Mm-hmm. Right.
So I have another question, but if someone else is
Yeah.
want to ask, then I will
any
wait.
question, Dr. Liu? You have a question?
I can wait. My question is a bit
Yeah.
different.
Okay. Who else has question? Yeah, maybe you can go, Yogesh. Yeah, go again.
Okay, so I think it's from your one of the slides, the last piece of work you showed, self-supervised.
Yeah.
So it was really nice at the end. You showed that those capsules are trying to focus on specific categories, like scene types you showed. So I wanted to understand, so this is like one level of capsules, but did you find any pattern, like maybe at a different level of capsules where they were focusing on not just at a scene level, but a very specific things?
Right.
For example, maybe color or maybe, yeah.
Yeah. So in this network, yeah, as you said, we only focus for this analysis on the final capsule layer. For this analysis. So because of the nature of this problem, what we had to do is basically for a video, we extracted, let's say for the video clip, we extracted a set of just a single feature vector. So that's kind of a global representation of the video. And then we made those into the capsules, into the initial capsule types. So already the initial capsule layer had a relatively global representation, right, of the video. So it would have been difficult to find, more, let's say, fine-grained representation of smaller objects, just because the nature of this problem, it's very large scale, so it's very difficult to get, let's say, capsule networks starting from just RGB images, let's say a single convolution and then a capsule layer. That would be very, I would say, impossible to fit into the current GPUs. Current GPUs. So for this reason, we mainly just found that the concepts that we learned were tended to be higher level objects or concepts. Yeah.
Okay, thank you.
So one question related to this transformer I have, Kevin, is see the transformer has this multi-head and multiple layer, then this position encoding, right? So I understand capsule have these layers, but how about these other things, the position encoding and multi-head? How do you, conceptually, how is it done in capsules?
So I'll start with the positional coding. So in the original work, in video capsule net, I didn't talk about it much, but there is a form of positional coding called coordinate addition. So in this case, given our vote matrix, we can perform coordinate addition by adding in the position of the capsule in the spatial temporal grid, right? So in this case, if this is the vote matrix, then we can add in the time coordinate, the height coordinate, and then the width coordinate to that vote matrix, and that will encode the position of that capsule for the routing algorithm. And we show that this coordinate addition actually improves results, and this is very similar to the positional encoding of transformers. For multi-head, so that is, one could say that's kind of analogous to the grouping of the capsules. I would say it's a bit different because ultimately we end up, it's a bit different. I suppose you could do multi-head attention, or it would be a bit difficult to do like multi-head attention. Well, So yeah, so I would say you can do multi-head attention for capsule routing, and we kind of do this in this final work. But in this case, we're kind of grouping already our grouped capsules. So we're like doing subgroups of the capsules, which is a bit kind of difficult to conceptualize. I mean, to kind of explain. So I mean, you could have multi-head attention to get these routing, or to do the routing, but there's not a lot of work that has been done, I guess, studying that. Yeah.
Okay, very good. So Dr. Liu, you have some question?
Well, I guess my question is quite different. It's not about detail, but it's more like on a high level, since you are already graduating with a PhD degree. I guess my question is, where do you see yourself in the next 3 years, 5 years? That's the first question. The second question is, you're working on a very exciting topic, and you probably are aware we have this fancy metaverse concept coming up. So I'm kind of curious, where do you see your PhD work contributing to having this virtual metaverse regarding mixed reality, augmented reality, virtual reality, so on and so forth?
Yeah. Okay. So I guess the first question: where do I see myself in 3-5 years? Well, so after I graduate, I'm planning to start working at Adobe as a machine learning engineer. So currently, I guess I'm still focusing on staying on industry. I guess that's my plan. I guess that's the current plan. Just trying to work on a lot of different problems. At a, let's say, larger scale, things that people can use. Not just writing writing a paper which may or may not get cited, right? I would like to work on something that has a broader impact, and that in industry. And how, I guess the second part is how I guess this work can be used in this augmented reality, mixed things like that. Yeah, that's a good question. I know that at least for the last work, using these different modalities can be very useful. So I know there's a lot of work coming out of Facebook dealing with this multimodal learning, just because if you're doing augmented reality, right, it'd be good to not just get video, but noise and things like the sound and things like that. So yeah, so whether or not these capsules can be really applied at this large scale, in the real world, is still a question that is yet to be answered. But I think this is, I guess, one step towards making capsules having capsules be able to be applied to such problems. Yeah.
Sounds
So
great.
Kevin,
That
maybe
sounds very exciting future.
Yeah, after working at Adobe a few years, you come back and become professor at CRCV.
Maybe, yeah.
Okay, so any other questions? So last chance. Okay, if not, then I think audience should leave. And so, Kevin, so you can make Dr. Awad